So next thing I want to do is just kind of catch up people on what the core technology is and why it is interesting, and of course what we've done in terms of the advancing the product since we last talked. And so when we founded PernixData, we founded it because we saw an irony in the storage industry, and the irony was that there was a lot of flash-based innovation going on, and there were vendors trying to make boxes, and vendors trying to actually fit in flash into a box that existed, and so on. So actually the projector now really needs work, but
I'll just let you know that in the video stream it's beautiful.
Yeah.
So the projector just must not be able to handle this.
No, and you are not seeing some boxes, which is a bigger problem. Yeah.
Okay,
can we
pause?
Can we grab a projector? Yeah.
Figure out what's going on.
I'm going to go ahead, but while they grab a projector.
Okay.
So I can do it without you can read my brain, right?
Yeah.
You can. Yes. Good. Good. So
don't need no stinking slides.
Exactly. So the irony we saw in the storage industry was that it was very clear that flash is the next level of innovation in storage. It was truly disrupting the physics of storage, and if the physics of storage are disrupted, then you can actually make something that didn't exist. But what was ironic was every time someone made something that didn't exist, it was in the form factor of yet another box. And that box was slightly faster and maybe slightly cheaper than the previous box that you were used to. And so it was ironic is that all this flash-based innovation was actually meant to solve one problem, and one problem only, which was the storage performance problem. But the storage performance solution came in the form factor of a box. That was ironic. So why was it that you had to replace your capacity if you are trying to solve performance? And that's why we founded PernixData. Is we thought that if you think about the storage industry as multiple different classes of people. There's a class of people who is for want of a better term called the legacy storage vendors, or the incumbents, sadly, for them.
Or the Evil Machine Corporation.
Yeah. Then there's a class of vendors who are called the hybrid vendors. They make a box full of spindles and flash devices. And there's a class of people who are called the all-flash vendor. They make a box full of flash and no spindles. And yeah, looks like we are just going to use a different projector.
No, shut.
Really, Howard?
Yeah, it's all the pineapple's fault.
That's all good, now I have some dirt on you. So those are typically the buckets, and so far, if you look at the evolution from the legacy vendors to the maybe the hybrid vendors, the all-flash vendors, yes, it has become interesting. Some data services have become interesting as now these new types of storage systems do data services that are much finer granularity. They can do it much more quickly. But at least from a solving the performance problem point of view, it is still a box which does a finite amount of IOPS. And the problem is that finite amount of IOPS, although it was bigger than the finite amount of IOPS that the older box did, is still not enough for the growth plans that you have. You'll add 6 more servers and then you're out. Or you'll add 20 more servers and you're out next year. So we're still chasing our own tail. And so the real problem to this solution is to actually solve the performance problem in a way that performance keeps on growing with CPU and memory. Every time you add a new server, you get an equivalent amount of storage performance. Now there was one type of vendor who actually did that, and who's still doing it, is this hyperconverged systems. Their story is that, well, the storage is part of the compute system, and so every time you add compute, you add some storage. Now of course there are some logistical problems, is maybe it is not worth adding storage every time you add compute, or maybe it's not worth adding compute every time you add storage.
Looks a lot better.
Cool. But there is one interesting thing in this box, which is which these other monolithic storage systems don't provide, is that this is the only one which has a scale out service processor. is with every compute node, you have a storage processor. And that, along with fast media, gives you scale-out performance power. And we don't even need to talk about capacity. In fact, I'm not interested. You know, it's as interesting as the elections going on in India at this point in time. So this technology advancement is interesting to the extent of, you know, bringing in scale-out service processing, which these technologies haven't brought, in my opinion.
SolidFire, you wouldn't say brings that kind of scale out? I mean, it's a dedicated storage device, but it's definitely scale out.
Oh yeah, no. So just to repeat the question, or maybe you're mic'd up.
Oh, we're all mic'd.
Good. So it is, and so what you're saying is you can actually increase the power of a box, right?
Well, you can cluster n boxes.
Exactly.
Up to
Yeah.
100 nodes.
Exactly. And so, you know, if I'm not mistaken, the numbers still don't work out to scaling out, you know, 100 flash devices and, you know, 100 servers. You know, the aggregate performance you get out of putting in 100 flash devices and 100 servers is still not. In fact, here's something ironic, right? You know, these boxes tend to contain more than one flash device, right?
Yeah.
So they contain like 20. And so why is it that a box that contains 20 flash devices doesn't do, you know, 20 times 100,000 IOPS, or, you know, 20 times? Because, you know, it is putting a lot of that processing power into data services, and which is fine. You know, it's a good thing to do.
Yeah,
But-
SolidFire specifically is 50,000 or 75,000 IOPS per node, and I think there's there's 8 devices, 8 SSDs in
Right.
each of the nodes.
There you go. So clearly you can do something fast, but, you know, the math of putting in some X number of flash devices doesn't translate to an equivalent output in terms of performance. And again, that is totally fine. It's totally fair, because you know, that horsepower is being used partly for data services, which is where it's being lost. But so then my point is, well, you know, you can have cheaper, wider horsepower for the performance part, and then you don't need to actually pay for that horsepower, which is slightly much more costlier than, you know, that horsepower which goes into the server tier.
Okay.
But good observation. I mean, there's also I think a huge religious debate about, you know, where flash belongs and so on.
Yeah.
So
We try
But-
to avoid metaphysics.
So if scale-out storage processing power is a real deal, if that is really what you want to get into a data center, and you don't want to really mess, and that has nothing to do with capacity, then we thought that there is a way to actually do it. And that is by, wow. Well, we'll get to that. But the way to do that is to maybe make a software layer that is an intermediate tier of data, and that intermediate tier of data runs on the server side and uses server components to solve just the performance problem and not the capacity problem. And so that was PernixData's core mission, is to bring scale-out storage to all these guys, you know. And it turns out that 85% of virtualized deployments, actually I should say VMware deployments, are here. And so, you know, if you really want to make an impact on virtualization by doing scale-out storage, then you can't make an impact by actually treating these guys as outcasts. You have to make an impact by actually making something that is usable by these guys. And of course, they can maybe grow out to use this. And so you also have to make a technology which is still relevant if they grow out to do this. So I'm not saying that the world should stay here. Maybe it goes out, you know, and gets here. But what I'm saying is scale-out storage ought to belong to everyone, not just the guy who decides to do this. And so that's what we are doing. And we are doing that by what we call the decoupled architecture, is we are using some server software and some server flash components to make a performance layer totally separate out from the capacity layer that you choose to use. And it is your choice. You can be on an EMC storage system, or you can be on a, I don't know, pick your favorite Nimble storage system. And it just works fine. That can be used for capacity, we can be used for performance. The way we do that is we created a piece of software that goes into the hypervisor, VMware for now. It is inside the kernel. So it's a wib that you install on ESX host through VMware Update Manager. And it goes into the kernel, takes control of the virtual machine's I/O path as it is going out to its primary storage system, and then uses a local flash device as a caching tier, as an intermediate tier of data. And so the idea is that, over time, all the hot data that the virtual machines are actually transacting move from this primary storage tier to this tier, which is made of software and hardware.
So is that write cache also?
It is a write cache also, and in fact, we'll get to that. But yeah, it is very important that it caches write as well. But first things first is it is a hypervisor component, so it is not a virtual appliance. We get hold of the virtual machine's I/O path right inside the hypervisor, not outside. It is not a new storage system that exports a NFS mount point or a SCSI mount point or whatever. It is the same old primary storage. If it's an EMC LAN, the virtual machine still thinks it's an EMC LAN, except it is magically faster. Or whatever. If it's a NetApp LAN, it's still a NetApp LAN, except it's magically faster. All the characteristics of that hardware system are still available to the hypervisor. For example, if it's a VII compliant device, all the VII commands that it responds to continue to work, and so on and so forth. So this is as transparent as it gets, and it is as high performance as it gets in terms of doing a caching tier of data. Now the second thing we did was we made it clustered. We made it truly clustered. Is as virtual machines move around, the problem is that this is a local piece of hardware. And so if you had actually established the virtual machine's working set out here on this local piece of hardware, as soon as the VM moves around, it just lost access to this guy. And so it's going to go out to its primary storage system to rewarm the cache, so to speak, out here. That's not interesting, because the problem that you set out to solve has come back up again as you are going to present traffic to the SAN. And so we made this system clustered. Is if the virtual machine moves around, it can still, FVP will still fetch on the virtual machine's behalf data out of any remote flash device that the virtual machine has cared to access in the past. And as it does so, it'll also warm up the media on the local server. So over time, you're not taking these network hops, you're just going local. And so you're back to square one. This is very important because now, we are going to a data center architecture where the hot data migrates up from the storage layer into the server layer and stays there. And that's very important. And then, it can go all across between servers, it doesn't matter, but it just needs to stay there because this is a much more scalable computing layer than this.
So is this done like every 5 seconds, Satyam, where you start moving data, or is it done real time as the IOs come in? Or?
It is done real time. So as the IOs come in from the virtual machine, we would fetch them. And that is very important too. Thanks for the question. Is that, if we were to prefetch the data, the thing is, these virtual machine flash footprints tend to be in the order of tens or hundreds of gigabytes, depending on the application. And so if you were to move 100 gigabytes of footprint over the network, well, first of all, you're going to kill the network. But more importantly, you're going to kill the flash device. And so you are writing all this data without a guarantee that the virtual machine is ever going to access it again. So we do it on demand.
But you're migrating data off of the primary storage.
Yes, and that happens.
Call migration. It's caching, right?
Cache, right?
Yeah, so it's on demand, right? So as the virtual machine
Copying.
Reads or writes data, the data is gradually getting into this layer.
Yeah, but it will write back to the primary storage.
Right, in the write back situation, which is what we are going to talk about now. And so it is very easy to understand how this can be a read cache. And so the third and the final thing I want to tell you about FVP and what makes FVP very special is that we solve not just the read problem, but the write problem as well. Is, we could use these flash devices as write caches. And you could do it on a per virtual machine basis. So you can have virtual machines in read-only caching mode, you could have virtual machines in write caching mode, read and write caching mode, whatever. Of course, most of our customers tend to just go read and write. Why would you choose
Some virtual machines don't have to be cached at all. I mean, you can disable the cache.
You can disable the cache too for some virtual machines.
Do you need to install something inside the VM?
You don't need to install anything inside the VM.
Cool.
So this is 100% hypervisor.
And can I programmatically change the state from write back to write through?
You can programmatically change any virtual machine's acceleration from write through to write back, or vice versa.
Write through to write back? Yeah.
Or write back to write through. You can programmatically add write replicas, which I haven't talked about, but I will in a second. You can enable and disable all these cache policies on a virtual machine without powering off the virtual machine. You can install PernixData without powering off the host.
Right.
And so, yeah, we can.
Do you provide a QoS mechanism of some kind? Like if I have all the resources available and all the machines go well, but then when I have lack of resources, I can switch off caching for someone automatically or whatever.
Right. So we are going to wait till the new technology section.
Okay.
The caching status moves with the VM as it's vMotion?
The caching states move with the VM on demand as the VM vMotions. So
Yeah, but I mean, if it's like read-write back, one ESX host, when it moves, it's read-write back the other
on
one.
the other one, yeah. And so let me, looks like there's some advanced guys, this is, but I'll subject you to 101 anyway. And so I didn't finish my write story, is that, when you choose to do write acceleration, the virtual machine would do a write, it goes to the flash device, it is acknowledged to the VM. And so with a net effect that the virtual machine, the application running inside the VM, sees true flash read and write latencies. And in the background, we are going to destage that data out to the primary storage system, and that might take more latency, but it doesn't matter. The application doesn't see it. Now, there is the obvious problem of what happens if the flash device fails while you hadn't gotten the data out to the SAN. And so to protect you against that on a per virtual machine basis, when you choose write back for a virtual machine, you can choose to have 0, 1, or 2 flash replicas for that VM. And so, for example, if you have one flash replica, then the virtual machine does a write, it goes to the local flash device, and it goes across the network, the server-to-server network, to a remote flash device. And only when both those flash devices acknowledge, we acknowledge the write to the virtual machine. Now, if one of the servers goes away, then the other guy, the replica, is going to make sure that the data still makes it to the SAN. And so now, depending on how important your application is, you would choose a degree of replication that you are willing to live with. Now, the interesting thing here is, clearly there is this question about, well, the data is going over the network anyway, so why not just send it out to the SAN? And it turns out that this network is a peer-to-peer network. It goes between 2 servers at a time in a cluster of 32 servers or whatever number of servers. And so that's a much more scalable network. It doesn't use a storage protocol. It uses RPCs that are PernixData proprietary. So it's a much lighter weight communication protocol than what you are using here. And of course, there's n entities trying to hit this one guy instead of this peer-to-peer scale-out model of doing networking.
Not to mention that we're assuming that guy is all spinning disks, so the write latency would be a lot higher.
Exactly. Write latency is a lot higher. And more importantly, these guys actually go crazy. If you treat them well, they're doing fine, and then you show them a spike in traffic, and then they just lose their mind. And so the idea about doing write back,
predictable performance storage on the back end.
Exactly. So the idea about doing write back is you don't present the spike in traffic ever to the storage system. You present a very uniform write out pattern to the storage system. And in fact, when we talk about some of the advanced technologies that we've been working on, this will become more and more clear. And so now the storage system can be designed for some X number of IOPS, but the real workload is capable of running Y number of IOPS, which is much higher. And that difference is made up by this layer.
Do you need one box per ESX server?
One.
Well, are
you talking about this box?
Yeah.
This is just a server. Actually, it has nothing to do with PernixData. We don't ship servers. Okay. So we only ship software, which is this box.
But
you add flash to that box.
You add flash to the server.
Okay.
That's right.
You do that yourself?
Yeah.
not something.
Okay.
They're not selling any hardware.
Yeah, okay.
It just installs into the hypervisor.
Right.
Okay.
I think Frank Deneman must be laughing his ass off right now because
Sorry.
he told me on this slide that, well, you know, the box makes it look like we ship a box, and you know,
He was right.
to Dutch people, it looks like
to
we
Dutch
ship a
people,
box.
yeah.
Exactly.
Although the running joke
That's true.
is
Oh, is
I'm
that-
also Dutch.
Really?
Free Dutch guys.
Well, free Dutch guys.
That's a conversation
yeah,
at the
absolutely.
end of the.
I see.
And Frank says, "Yep."
Oh, yeah. Bastard.
At least he still has a job.
So, well, I'm going to ask him to make me an icon that is not this server. He brought it to himself. So anyway, you know, that is what the software does. But what we are actually out to do in virtualized data centers is that we want to fundamentally change how you architect the storage system, the storage infrastructure in your data center. Is we want to actually make you architect a storage performance layer consisting of server-side components and software, totally separate from your storage capacity layer. And so buying capacity now becomes a no-brainer. You go with any vendor that gives you, you know, gigabytes at good price and with good data services. And that is an incredibly cheaper problem, and it's an incredibly easier problem than actually architecting these boxes for performing well.
Can that storage be like something like vSAN or something like that? Do you care?
What was that again?
Can it be vSAN? Or?
Well, vSAN falls in this hyperconverged bucket where, you know, they are vying for that server-side flash that we are using too.
Okay, so they
And
do.
so, you know, in some sense, it's
and-
a
and-
exclusive thing.
And they're also write caching and replicating.
That's
So
right.
you would be sending all the data across the network 4 times. It's like theoretically would work, practically not a good idea.
I haven't used it myself, but, you know, I trust your. I like this other thing, you know, it's called FAB. Did I tell you about it? It's awesome. And I get it for free. So anyway, but to your question, you know, one way to look at it is this is a vSAN for every guy who is running a shared storage system, right? And what is vSAN? It is a scale-out processing model. It is a scale-out storage processor, which is trying to, you know, make performance scale out along with compute by using server-side components. That is exactly what we're doing. And we are saying on top, what we're saying on top is that, well, you know, to do that, to get that goodness, you don't necessarily need to throw out the bathwater or the baby, whatever.
Something
one
like
of the
that.
two.
Yeah.
So that's our story so far. Some of you are already familiar with it, so hopefully nothing too outrageously, you know, surprising here. But any questions?